represent the continuous time signals in terms of impulses. Now, if you recall previously, for discrete time signals or sequences, we express any arbitrary sequence in terms of unit impulses. Okay, so these are also discrete unit sample sequences that exist for one discrete time index. So in this case, delta n minus k means that this sequence is going to exist for n equal to k only. Okay, so that means if you expand this for a few terms, well, that can be expressed as, let's say, dot 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 plus x of 1 or x minus 1, let's say minus 1, then it will be delta of n plus 1. Okay, then this is for k minus 1. Okay, this expansion is for k minus 1. Then plus, let's write few more terms. For k equal to 0, this will be x0, then delta of n. Okay, plus, so another term, let's bring another term. For k equal to 1, okay, this is k equal to minus 1, this is k equal to 0. For k equal to plus 1, this will be x of 1 into delta of n minus 1, and then this sequence continues. Okay, so if this is in general an infinite sequence, infinite discrete time sequence, then any arbitrary sequence, any such arbitrary sequence can be expressed or expanded in terms of discrete time or unit sample sequence x delta of n. Okay, and you see that in this expansion, the weights of or the strengths of these impulses are precisely the samples of x of n. Okay, these are x of, so x of k is varying from minus infinity to plus infinity. So for example, whatever is the sample at let's say discrete time index n minus 1 will be this can be expressed as x of minus 1 multiplied by delta of n plus 1. Well, what it means is that since the delta function only exists at one discrete time index, and in this case this is existing at n equal to minus 1 only. Okay, then let's say you have another sequence at n equal to 0. Okay, then that will be the second term, which is x0 having a weight x0 multiplied by delta of n. So of course you see delta of n only exists at n equal to 0, otherwise it is 0. Okay, then similarly for third sample, call it n equal to plus 1, this will be existing at plus 1 only, or 0 otherwise. Okay, so this sequence continues. So the thing is, you can express, so at n equal to 1, this has a weight of x of 1, which could be positive or negative, but this is a unit sample having a weight of x1, and then this is multiplied by delta n minus 1. Okay, so any discrete time sequence can be expanded in terms of delta functions. Okay, so you see this corresponds to the representation of an arbitrary sequence as a linear combination of shifted unit impulses delta n minus k, where the weights in this linear combination are xk. Okay, so the weights are xk, and xk are precisely the samples of x of n, x0, x1, x2, or x minus 1, x minus 2, etc. Okay, k is varying from minus infinity to plus infinity in general. It could be infinite sequence. So the above equation is called the shifting property of discrete time unit impulse, because the sequence delta n minus k is non-zero only when k equal to n. So that means the summation on the right hand side of the equation shifts through the sequence of values x of k and preserves only the value corresponding to k equal to n. So this summation on the right hand side is only non-zero for the values where k is equal to n. Okay, so you have the strength of the impulse x of k there. Okay, and these x of k are the samples of your sequence x of n. Okay, now what we do is similarity and deriving an analogy to discrete time sequences, we consider continuous time signal and see how we can represent this in terms of pulses or continuous time impulse functions. So what we can do is, so if we think a unit impulse as an idealization of a pulse which is so short that its duration is inconsequential for any real physical system, we can develop a representation for arbitrary continuous time signal in terms of these idealized pulses with vanishingly small duration or equivalently impulses. So what is happening here is, for example, let's say you are taking samples, okay, of a continuous time signal x of t, and in between these samples, you are approximating this with a staircase-like waveform. Okay, so for example, for any such staircase, for example, over here, has a finite duration delta. Okay, this delta is infinitesimally small, but its height is also represented by 1 over delta. Okay, so 1 over delta. So for a continuous time signal, we are trying to derive an analogy such that we can have an expression xt which should be expressible in terms of continuous time impulses. Okay, so if you want to define a continuous time impulse, let's say of a finite duration delta, okay, this is also delta, this is small incremental delta, then this can be expressed as um, 1 over delta, 1 over delta between, call it 0 to t to delta. That means for a finite but a small duration of delta, this function exists, okay, and it is a value of 1 over delta, and it is 0 otherwise. So that means we can have the representation of the signal xt in terms of such direct deltas functions. Okay, so to develop the continuous time counterpart of discrete time shifting property, we begin by considering a pulse or a staircase approximation xt to a continuous time xt as illustrated in 2.12a. So we have a staircase form of an approximation where each pulse has a finite duration of delta, and it has a amplitude of 1 by delta. Okay, what it means is that if you look at this delta function, okay, this is my delta of the subscript is again delta, triangular delta, then this is t. So well, the duration is finite. Okay, it's of interval, it exists between 0 to delta, so the duration is delta, okay, and the height is 1 over delta. Okay, that means the function has an area, or the area of this rectangle is 1. Okay, that means you take the if you integrate this with respect to time from 0 to infinity, okay, 0 to infinity or 0 to delta, okay, you take the area of delta t dt, that's unity. Okay, dt is unity. So this function is defined in terms of its weights, and if you compare this with the delta function, an impulse in continuous time domain, well, you can derive delta t in continuous time domain by considering the limit that delta approaches small del, the finite duration pulse. If this pulse approaches 0, okay, and if you apply this limit over this expression, then this precisely becomes the definition of delta t function. Okay, delta t will only exist at t equal to 0, and it is 0 otherwise, but at t equal to 0 it's infinite. Okay, so 1 over 0 is infinite, it's not defined at t equal to 0, so the function is not defined in ordinary sense. But however, if you want to talk about this xt in terms of delta t, well, one way to look at this is that, okay, if you consider a piece of signal, okay, let's say this is my, okay, call it f of t. Okay, now you have f of t, and this is the time axis, and your delta t exists at a certain interval. Let's say it is shifted by tau, so this is minus tau. All right, and this is somewhere, this is 0. Okay, so f of t is existing throughout the time for minus t to plus t, right? So what happened at this point? Well, this point at this point means that the impulse is going to have a weight of f tau, okay, because at this point how you express the multiplication is that this will be f of t, I mean the product of f of t into delta t minus tau. The product is nothing but this equals to f of tau delta t minus tau. You see, the idea is that delta t minus tau only exists at t equal to tau. Okay, this exists at t equal to tau, and it is zero elsewhere. It is zero elsewhere. Therefore, if you multiply these two time domain signals, this is an impulse, time domain continuous impulse delta t shifted by tau. If you multiply this with f of t, then that means this will be f of tau delta t minus tau, okay, because otherwise the function has become 0. So at particular instant of t equal to tau, the weight of the impulse is f of tau, okay, which means if you take the area on both sides, if you integrate this with respect to time, what you get is f of tau. Okay. So that's the strength of the area underneath the curve, okay, and because integration of delta t minus tau is 1, okay, and since this t minus tau, this exists at t equal to tau, you can take I mean if you integrate this, for example, even with respect to the dummy variable tau, this can be f of t, you can or this is integration with respect to t over here, you can take f of tau outside of the integration, then you're left with delta t minus tau, and that integration, by definition, this is equal to 1, okay. So this is again the strength. You're left with the strength of the signal at that particular instant t equal to tau, okay. And you see there is a very striking similarity between this expression and what you have over here. I mean, let me put this expression over here. So if you want to write this as f of tau, there is this continuous time signal f of tau delta of t minus tau. You see, if you take the, I mean, in delta function, if delta function has infinitesimally, if it exists for infinitesimally small duration, and it has a infinite height, but it's defined in terms of its weight, such that delta t dt is unity, well, then this is equal to f of tau, okay. So if you are going to integrate this from minus infinity to plus infinity, you see that this has a very similar representation to the discrete time case, okay. This is again the strength of the impulse. The strength of the impulse over here for the digital impulse is the sample of the sequence x of n. But over here, the strength of the continuous time impulse is the value of that function, continuous time function f of t, at that particular instant where the impulse exists, okay. So this is the analogy. This is how you are going to express your signal f of t over here in terms of the continuous time impulses, okay. So let's try to understand this in a little more detail. You see, for example, now you have a series of staircase impulses, and delta is a very small, infinitesimally short time period, okay, such that the area of any impulse, area under any impulse, is unity. You take any impulse, the finite duration is again delta, and the height is 1 over delta, okay. So for example, x minus 2 delta, again you see the duration is delta, the height is 1 over delta, so the area will be equal to x minus 2 delta, okay. Similarly, the area, the strength will be x minus delta, okay. So you are shifting, it's just like shifting the impulse, it's looking like a staircase impulse, and this is shifting through the sequence, through the signal x of t, okay, over the x is t, and let's say at any particular instant k delta, the area will be k delta. For example, over here you have another impulse, okay, the area will be k delta, this is k delta, okay. So over here, for example, this is again the duration is from minus delta to 0, the value of the function at where the product occurs of the impulse versus the multiplied by the signal xt at that particular instant in time, that is x minus delta. Okay. Similarly, for 0 to delta, the product is x of 0. Similarly, it is x delta for delta to 2 delta. Okay. So again, you see, you can try to express xt in terms of continuous time impulses, just like you can do that in a uh, discrete time sequences. Okay, so any arbitrary discrete time sequence is expressible in terms of uh, discrete time impulses, the linear combination of discrete time impulses whose weights are the samples of x of n itself. Okay, similarly, you can express a continuous time signal in terms of the continuous time impulses delta t with the weights which are precisely equal to the value of the signal at that particular instant where the delta t exists. Okay, for example, this exists at minus 2 delta, so this is minus 2 delta. This exists at minus delta, so this the value is x minus delta, and this is the area. Okay, this is the area under the curve. So the definition again of delta function defined over here is, now you see, if you put a limit of this limit that this duration is infinitesimally small. Okay, so if you say that the limit that this delta approaches 0, okay, we put the limit over here, this implies delta t. This is the impulse which exists at t equal to 0, having a weight of unit or unity. Okay, delta t dt is 1. It's 1. So in manner similar to that employed in a discrete time case, this approximation can be expressed as a linear combination of delayed pulses as illustrated in figure 2.1 to A to E. So these are figure 2.1 to A all the way to D, E, and they are showing that in terms of delayed pulses, the signal xt is expressible. Okay, so that the areas under each pulse is the strength of the signal at that particular instant where the pulse occurs. Okay, so now if you use this function, for example, then if you don't use the delta t directly, okay, if you make use of this pulse, then since delta of delta t has a unit amplitude, okay, the product of delta multiplied by delta of delta t from the definition, you multiply this, then this duration, the weight or the area under the pulse is unity. Okay, so we have the expression, we can have the expression for xt as, so this is an approximation, this is x hat of t, this is an approximation of xt, which is equal to, can be written as k minus infinity plus infinity, and then you sum it up for over all the values of uh, k delta. Okay, so wherever the impulse exists, it will have the strength of xk delta. Okay, for example, what is happening over here is that this is minus 2 delta, so your signal value is taking the argument, it takes the argument minus 2 delta, and whatever is the value of x minus 2 delta is the weight or is the area under this pulse. Okay, similarly at minus delta you have x minus delta, at 0 you have x0, at delta this is x delta. So if you sum it up from k equal to minus infinity to plus infinity, you expand this for uh, few terms. You can write this as, for example, this will be x0, okay, then delta t delta, so there's a delta over here as well, delta plus, let's expand this for one or two terms. This will be x of minus delta over here, minus delta, then delta of delta t, so k is minus 1, k is minus 1 now, so this will be d plus delta into delta. You see, the product is unity. Okay, the product is unity, so you're constructing the entire signal xt as a summation. Okay, and then you have over here is x delta, k is 1, so k is 1, so it will be delta of t minus delta, into delta. Okay, plus dot dot dot. It's continuous. So you see, again, we are trying to express, we're trying to make an analogy between the discrete time case and the continuous time case by considering the delayed impulses, the delayed pulses, okay, which again have an area of which have an area of unity. So from figure 2.12, we see that as in the discrete time case, for any value of t, only one term in the summation on the right hand side is non-zero. Okay, so wherever the pulse exists, you have the strength of, or you have the value of that signal at that particular instant. For example, over here, that instant is delta. Okay, that is minus delta. So you have the value of that at particular instant x minus delta. Similarly, since delta t exists at 0, so the signal is going to take the value whatever is there at t equal to 0. Similarly, this is at t equal to delta, so you are going to have the value of the impulse is going to exist at t equal to delta. Therefore, the value of the signal will be x delta. Okay, whatever is the value or the amplitude associated with the signal x of t at t equal to delta. Okay, then as we let delta approach 0, the approximation xt becomes better and better. So that means you have a very fine steps. So they can be, and if delta is approaching 0, that means you just have a large number of samples. You just have a very huge number of samples that you're going to add up, and the natural transition will be an integration from summation. Okay, so the left hand side won't be x hat, it will be xt. As delta approaches 0, the approximation becomes better, and in the limit it equals xt. Okay, therefore limit delta tends to 0, well, this becomes delta t. Okay, so you will see over here, when this delta approaches 0, well, the approximation will be an integral. So approximation is an integral over here. Okay, so the thing is, because you see over here, even delta t minus tau means that this delta function is going to exist at t equal to tau only. Okay, which means this can be written as x of t. Okay, this is an exact representation of the continuous time signal in terms of shifted impulses, and then you have this delta of t minus tau. So this is the shifting property in the continuous time domain. Okay, just like you have this in the discrete time domain with summation, here you have an integration. Okay, if the pulse duration is infinitesimally small, and you can take this xt now outside the integration is with respect to the variable tau, so you can take this outside of integration. This becomes x of t, then under the integration you have delta of t minus tau d tau. Okay, tau d tau, and you see this impulse is always defined in terms of its weights, and the area is unity. So this whole term goes to 1, and on the left hand side you're left with, on the right hand side you're left with xt, which is equal to xt over here. Okay, so that's the representation of continuous time xt in terms of the shifted pulses when the duration of the pulse is approaching to 0. Okay, so the summation naturally approaches to an integration, and this approximation is not x hat of t, this is xt. This becomes accurate, this becomes precisely equal to xt. Okay, now this can be also be seen by considering the graphical interpretation of the equation as illustrated in figure 2.13. Now what happens in 2.13 is you have a signal x tau, then delta t minus tau again. You see the duration is delta. Okay, and let's say m delta is greater than, let's say it's a value of time. Okay, so it's greater than t minus delta, but it is less than the present time instant t, let's say. Okay, so you can say that this is a shifted pulse, again having the the area is again 1. Okay, the height is 1 over delta. Okay, because this rectangle has a height of 1 over delta, width is delta, so the area is 1. Okay, but you have a shifted impulse in part B, and you have a continuous time signal in part A. In part C, there's a multiplication of the two signals. Okay, so this multiplication is only non-zero over the interval, over this interval, t minus delta up until t. That means if you multiply this over this interval, well, this has to be straight line, but anyways, so there will be a rising trend of the signal. Okay, that is contained over here. You can see this this rising trend of the signal. This was the impulse which is shaded part. Okay, exists from t minus delta to t at m delta. So this signal is going to take the value m delta, right? I mean, this because the impulse has been shifted at m delta or k delta, whatever it is. Okay, so that means multiplication of this impulse x tau multiplied by delta of t minus, well, t minus tau is precisely will be equal to the value x of m delta. Okay, why? Because the pulse is only existing from t minus delta to t. Okay, again a duration delta, but the value of the signal is going to be present at m delta only. Okay, so the value of the signal is going to be present at m delta. So this is x m delta, x m delta. Okay, this is x m delta. The height is x m delta, x m delta. So you can multiply this with delta of t minus tau. Okay, basically it exists at m delta. Okay, it exists at m delta. That's the idea. So you see, we illustrated the signals. So in part A you have x tau, then in part B you have a shifted pulse, and then you see their product. So we have also indicated the shaded region whose area approaches area under xt, delta t minus tau as delta approaches 0. Note that the shaded region has an area equal to x m delta, where t minus delta, where the finite duration exists from t minus delta to t. Okay, so over here you will have an amplitude equal to xm delta. Okay, so that's exactly the point where the pulse exists. Okay, and delta is infinitesimally small. That's the point where the pulse exists. This is the point where the pulse exists, and at that point you will have the value of the signal, that will be x of m delta. Okay, and otherwise the product is 0. Otherwise the product is 0. Okay, otherwise this product is 0. This product is 0 otherwise. If this is not the duration, then this product is 0. Okay. So furthermore, for this value of t, only the term with k equal to m is non-zero in the above summation, and thus the right hand side of the equation is also equal to x m delta. Consequently, it follows from the above summation and from the preceding argument that xt equals the limit as delta approaches 0, the area under xt delta t minus tau. Moreover, we know that the limit as delta approaches 0, it becomes a unit impulse function. So consequently, we can write xt as such. Okay. So what it says is, if you are going to take the area, okay, if you want to take the area with respect to tau, then the area is nothing but the strength of the shifted pulse. And guess what? The strength of the shifted impulse is x of m delta. Okay, x of m delta. So as a limit, delta approaches 0. That means you can write this this graphical interpretation in analytical form in terms of the continuous time impulse which exists at t equal to tau. So you can express your any signal in any arbitrary continuous time signal in terms of delta t in terms of shifted impulses, just like as in the case of discrete impulses. Okay, so this is the representation of any arbitrary continuous time signal in terms of shifted impulses, and the definition follows from the fact that the area under the continuous time impulse is unity. Okay, it's unity. So this the left hand side and the right hand side are equal. This is again xt. So xt can be expressed in terms of shifted impulses, just like we had this in the discrete sequence representation in terms of shifted discrete time impulses. Okay. All right. Now, as in the discrete time, we consider the shifting property of the continuous time impulse. We note that for a specific example, if xt is ut, this can be written as, for example, if now if you have a sequence ut, so how you're going to express this in terms of shifted impulses? Well, just plug in over here for x of tau. You have u of tau, and you notice that the step signal, it is 0 for t less than 0, and it's 1 for t greater than 0. So you just modify the limits, and as a result, you have this. The integration is this integration is representing ut. Okay, and if you recall, we have a very similar expression in discrete time case in terms of unit impulses. U of n was expressed as delta of n minus k. Okay, there was a summation. So if you sum them up from, but k has to vary from 0 to infinity.